recording. What's that? Oh, that's you? God, I'm kidding. I'm kidding. So that's all right. But what I was saying is just a reminder. So I've shared this with you guys before, but it's worth sharing again. So, and this is good for all your classes. If I go to the internet, and if you guys go to, let's see, if you go to the internet or anywhere, but if you go to the internet, the registrar has a homepage. And if you scroll to the bottom, and this is true every semester, they have a PDF of the final exam schedule. In particular, this semester, because we started early and we're kind of ending differently, you got to pay attention to this. And they're asking us to stick with this as much as possible. And so what you'll notice is our class meets Monday and Wednesdays at 11. So our designated final time is that Monday at 11 o'clock. So it's going to be a take-home exam, but in order to sort of appeal to the wishes of the school, and it's also more fair for you, we're going to have a more strict, I'm not just going to give it to you and say that you have a week, like, right? We're going to have a more strict sort of time frame on it, but it will be just like before. So, yeah. Yeah, so it's going to probably be something like that. What I'll probably do, yeah. So I'll post it. I'd prefer not to do it that way because I'd like to give you time if you're going to have questions to do it. So what I was thinking is I was thinking the following, and if this is messing with anybody's schedule, well, please let me know and we can try to accommodate. So our final is take home. And so the goal is, or the idea is that I'll post it on Monday, at 11 a.m. And then it's due, or it will be due. And I'll repeat this going forward. So, but it's due the next morning at 11 a.m. So you'll have 24 hours to do the exam. And you shouldn't, it's not going to take you 24 hours, but I'm giving you that amount of time. It better not take you 24 hours, not if you're prepared. So you can imagine it'll look very much like the midterm. And I'll try to make it as fair, but also is this stuff is challenging, so you shouldn't expect an easy exam. Does anybody have any questions about this at all? Anything? All right, so all right, let's pick up then where we left off. So what we've been talking about, someone has a pregunta. I have no idea, Michelle. Zero. You're way too far ahead right now. I couldn't tell you. I mean, I haven't even constructed it yet. I'll know more about the specifics of it closer to the exam time. So yeah, I can't answer that right now, unfortunately. I would imagine between 5 and 10 questions, give or take. All right. So what we've been talking about is division and modular arithmetic. So we're going to pick up with that. So So we've been discussing division and modular arithmetic. So, and the payoff is going to be hopefully that what's not hopefully we're going to do it is we're going to talk about cryptography, which is the science of codes and secret messages and stuff like that, which is the basis for how in a digital world we do things safely, securely. Okay, so very good. Okay, so today we're going to take these ideas and we're going to go a little in a direction that some of you might be familiar with, some of you might not be familiar with. So today we start with a discussion of representing integers. So this might seem like a weird thing to say, but it turns out that when we do this, and some of you are familiar with this. In fact, if you've had any experience with coding or the science of programming computers and how they work, you'll understand that computers work in what we call binary number system. They use 2 digits, 0 and 1. Us humans, we tend to operate best using 10 digits, 0 through 9. That's how we construct our numbers. And there's lots of reasons why we might think that one's better than the other, but for humans, it seems natural to us. We have 10 fingers, 10 toes. It seems like a pretty simple way of counting. But is it the best? I don't know. I mean, if you study the history of civilization, you'll know that humans for a while used all kinds of different representations of numbers. Base 8, maybe base 60, was, again, I don't want to get into the history of math, but the different cultures and peoples use different number systems. And we've only been using the number system that we currently use for, about 800 years or so. That might seem like a long time, but in the big picture, is it really a long time? Right? So, but anyhow, we want to talk about some other sort of ways of studying numbers, excuse me, not studying numbers, but well, we will study, but representing numbers. So, one thing I would ask you to do is this. Suppose today is, well, what's today's date? 11/6. Okay, that's too big of a number. Let's take something not so big. So consider, this. It's funny, actually, this is great because I was taking Lydia to school this morning. She goes, Daddy, is 1,000 bigger than 100, right? And I go, yes. And she goes, why? Like, see, we take for granted numbers. Like we just do. We don't realize that there's so much, our number system is just symbols that represent something, right? They're abstract symbols. So if I consider how many days are in a year, let's say 365. This is an abstract symbol. If I said to Lydia, what does this mean? She would say 365. She doesn't get the context that we are taught, the convention, that's not 365, that's 365, right? She's 5 years old. She doesn't understand that yet. Like every morning, Amy makes her write the number of days of school. Like today was the 47th day. So I'll be like, Lydia, write 47 on a sheet of paper, and she takes a picture. And she says, what's 47? I say, it's a 4 and a 7. And then she goes, oh. And I say, make sure you put them next to each other so we know that it's not 4 and 7, but 47. But she doesn't get what 47 means. She can say it, but she doesn't understand it. And so if I say 365, well, what does this mean? Well, by definition, it means 365, really by definition, this is a shorthand for 3 times 100 plus 6 times 10 plus 5 times 1. So when you were children in school, you learned about these place values. You learned about tens, hundreds, thousands, etc. Yeah, right. So that's a good thing, Mackenzie. Like one of the jokes with kids is if, a kid will get a dollar bill, right? And then, my uncle used to do this. He said, I'll trade you, right? I'll trade you, 3 quarters for a dollar bill. Well, a kid will normally think 3 is bigger than 1. So they'll say, I'll take it, right? And then you might say, well, I'll trade you, 7 dimes for your 3 quarters. And they're like, well, 7's way bigger than 3, right? So we sometimes forget that even though the numbers are natural to us because we've used them all the time, they're not natural, right? It's not, these are symbols. So it's different, no crazier than 365, in which you guys have no problem understanding. Think about this. What does square root of 3 mean? I mean, this is an abstract symbol. It represents something. What does it represent? So you got to be careful with how you define these things. Anyhow, I hope you ponder that. Another way to think about this is that this is 3 times 10 squared plus 6 times 10 to the power 1 plus 5 times 10 to the power 0. Now that seems like a weird way of writing, but we can do that. So here's a fact that maybe you know, or maybe you don't know, but it turns out we can do this with any integer. Well, I guess positive integer. Not just 10. I mean, think about how we count. Think about the first way you learned to keep score when you were a child. You tallied, right? The first thing you learned is you would do things like this: 1, 2, 3, 4, 5, 6. And you say, well, that's ugly. So maybe what I'll do is I'll group them by 5s or by 10s. That's what we do. And then we create symbols to represent these things because it gets unwieldy. So let's illustrate on a number that's not 365, because that's going to kind of be buggy. Let's take a smaller number. So let's consider something like, I like this number, 23. Suppose I don't want to write it as powers of 10, but I want to write it as powers of something else. So being that this is a class in computer science and binary is the language, and I know we haven't defined it yet, but binary, you might understand, means 2. The decimal, the previous page, the base 10 that we use, we call that the decimal system. Decimal, 10, deci. So let's consider 23. Maybe I want to think about how it works with powers of 2 instead of powers of 10. So on one hand, look, on one hand, you could think of this as 2 times 10 plus 3 times 1, right? Or I might ask myself, I might say, self, how many groups of 2 go into 23? Now, you might not want to think of this way, but that's what I'm writing above with 2 times 10. I'm saying how many groups of 10 go into 23? And then what's left over, right? So now think about that division algorithm we talked about last class. How many groups of 2 go into 23? Now, you have to be careful. Because if we just do groups of 2, that's not going to be, okay, let's just say we're going to do groups of 2 first. So how many groups of 2 go in there? You would say 10 times 2, right? And then what's left over? You would say 3. And then you could say, okay, well, how many groups of 2 go into 10? Well, you could say, oh, there's 5. So this is 5 times 2 times 2.
Why wouldn't we do
the only way to think about this? I'm trying to think of this, trying to get you to think about a natural way to ask how many groups of 2 go into something. And then you might say, well, how many groups of 2 go into 3? Well, 3 is 2 plus 1. And then I might play the game again. And I'm not saying this is an efficient way to play the game, but I say how many times does 2 go into 5? Or how many groups of 2 go in there? Well, I can rewrite 5 as, maybe I write it as 2 squared plus 1. Now that might seem ridiculous, but I can do this. And then over here I have 2 plus 1. And then if I just do a little bit of arithmetic, I notice that what I have here is 2 squared, and then this is also 2 squared. So what I get is I have 2 squared plus 1 times 2 squared plus 2 plus 1. Or another way to write this is 2 to the power 4 plus 2 squared plus 2 to the power 1 plus 2 to the power 0. So that, again, that seems silly, but we could definitely do it. And you could verify for yourself that that is in fact correct. So I'll let you catch up. And then if you have a question, please ask. Now, another way to see this, which is different than what I just did there, is I can ask myself the following question. So let's study this from a different perspective now. Now I take the 23 and I might ask myself the following. I might say, what is the largest power of 2 that I can, or that I can divide into 23. So you have to ask yourself, what are the powers of 2? 2 squared is 4, 2 cubed is 8, 2 to the 4th is 16, 2 to the 5th is 32. So I can only do 2 to the 4th. So I can think of 23 as 2 to the 4th, which is 16, plus what's left over? What's the remainder? Well, the remainder would be 23 minus 16 is 7, right? And then I play the game again. What is the largest number? Or excuse me, what is the largest power of 2 that goes into 7? And I get 2, right? So I get 2 squared. That's 4, and then that's plus the remainder is 3. And so I can keep playing this game. And what's the largest power of 2 that goes into 3? Well, that's just 2 to the power 1, and then that's plus the remainder of 1. And so finally, I can write this as 2 to the 4th plus 2 to the power 2 plus 2 to the power 1 plus 2 to the power 0. So again, this is completely analogous to what we did with 10. We wrote it instead of writing 23 as powers of 10, we're writing it as powers of 2. Now, the key observation is to think about what are the coefficients in front of these powers of 2. What number is here? Well, there's the only number here, which we technically didn't write, but we could write this in the following way. So notice, and now this seems silly, but we could write 23 as 1 times 2 to the 4th plus 0 times 2 cubed plus 1 times 2 squared plus 1 times 2 to the power 1, and then 1 times 2 to the power 0. That seems silly, but what we can do is we can definitely think of it that way. Now, these coefficients they give us an alternative way to write 23. So 23 equals 10111. And what we do, we can say in binary. So the number 23 that you know and love with a 2 and a 3 has another way of being described. It is 10111. And this is completely analogous to what we did before, as opposed to 23 equals 2. Why? Notice it's just 2, 3 in decimal. Notice the analogy. Where does the 2 come from? Well, that's how many powers of 10 to the 1, and this is how many powers of 10 to the 0. That is some very good you-know-what, Mackenzie. Way to pretend like you're having fun. Now, and I'm going to show you a way to teach this to kids in a second, because this is hard to learn. Most of us struggle with this. Now I'm going to show you a real easy way that it makes it easier for you to understand this. And we can do it with any base. I'm just working with 10 and 2s right now. So there's this cool mathematician out there. His name's James Stanton. You can Google him. He's not hard to find. And he had this game that I don't know if he invented it or what, but he made it known to me. And he called it exploding dots. And it was a way to teach different base of numbers to children. And it actually, you can take these ideas and expand them to all different places in algebra and stuff like that. But I just want to show you number-wise. So let's think about how a kid might ponder this. And without knowing all this sort of arithmetic and exponents and all that crap, let's think of it in a different way. So imagine what I'm going to do is I'm going to work sort of in an interesting way. I am going to do the following. I'm going to make a sort of a game table, and over here what I'm going to do is I'm going to have 23, but I don't want to write it in any other way than the most natural way that a kid knows. My kid knows that 23 means she has, if she counts 23 of something. So let's imagine we have 23 of something. So that's, let's do, what's 23? We can think of that as 4 rows of 5, right? That's 20. So there's 15, there's 20, and then we have 3 left over. So that's my 23 of something, right? Now, what I'd like to do is I would like to group them by 2s. Right now, if I group them by 10s, I'd have how many groups of 10? I'd have 1 group of 10, 2 groups of 10, and 3 left over, or 23. But let's suppose I want to group these guys by 2s. How many groups of 2s do I have? 2, 2, 2, 2, 2, 2, 2, 2, 2, and 2. And then we have 2 right here. I think we did that, didn't you? Yeah, this is a pretty cool thing. Now, what I'm going to do is, the way this works, if he had his game on his website where once you group them, they explode and 2 become 1. So each one of these groups of 2 becomes 1. So in the next sort of box, if you will, let me write this down. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So how many groups of 2 do I have? I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I need 11 dots plus 1. So how many are left over at first? There's 1 left over, right? So I'm going to put a 1 underneath there. Now I'm going to group these guys again. So I have my 11. Notice I have 11 green circles over here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? And so over here, let's make sure I have 11 dots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Great. Now I play the game again. Group them by twos. So when I group them by twos, how many groups of 2 do I have? Well, I have 1, 2, 3, 4, 5 green circles. So that means in this box, I'm now going to put 5. 1, 2, 3, 4, 5. And I also note how many are left over in the second bin. There's 1 left over. So I play the game again, group by 2. 1, 2. There's 1 left over. So I draw my bin and I play the game. How many dots should I have here? I should have 1, 2 dots because there's 2 green circles. And how many are left over here? There's 1. Play the game again. How many groups of 2 do I have? I just have 1 group of 2. So what do? That means I draw 1 dot here. How many are left over in this bin? 0. Can I group by 2s anymore? No. So how many are left over? 1. And now you'll see 1, 0, 1, 1, 1, which is exactly what we got before. And whenever I saw this for the first time, I was like, oh my God. Now this works with any number. You could take any. You want to draw a bunch of dots and do this, you can do this. Now, of course, this isn't efficient, but you can do it. Well, yeah, but I didn't want to say that. Friggin', huh? Friggin'.
Yeah, I wasn't sure where this was going
Yeah.
at first, but.
So it turns out that this is true, and we can do this. There's actually a theorem, but we're not going to prove it, but there's a theorem that says you can do this for any positive integer. You could do it for base 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, what's beautiful about this, and really any base, it doesn't have to stop at 10. What's beautiful about this is when you recognize that you can write a number in any base, it turns out you can learn a lot about numbers, what divides into them. Do you guys remember learning things as kids? You might have learned like tricks to see if a number divides another number. Like, how do you know if 3 divides something? Well, one of the tricks you learn is if you add up the number and the sum of the digits is divisible by 3, then the number is divisible by 3. So for example, take a small number, 27. Is 27 divisible by 3? Turns out it is, but one trick way you can know that real quick is you take 2 and 7 and you add them, and 2 plus 7 is 9, and since 9 is divisible by 3. There you go. Okay, so let's write this down. So here's a very important theorem. So suppose B is any integer greater than 1 and n is any positive integer. So there exists a unique expression n equals a sub k times b to the power k plus a sub k minus 1 times b to the power k minus 1 plus dot, dot, dot. This pattern goes all the way down to power 1, and then, of course, plus a number, an integer. And what can we say about these numbers, these letters? Well, where k is a non-negative integer, and a sub 0, a sub 1, a sub 2, all the way up to a sub k. And the only thing is we restrict a sub k from being 0. And these guys are less than b. So you notice in the previous example where we did base 2, those coefficients were either 0 or 1. In base 10, they can be 0 through 9. So there's a name for this. So we call this the base B expansion for n. Does anybody have a question about this? By the way, it's not worth your time to memorize this. This is a theorem that says you can always do it. What you should practice is being able to do it without having to go to Google and asking yourself, what is 39 in base 4 or something. Now, of course, you can use Google to check your answers, but you should know how to do this because it's really, these expansions in different bases, really the patterns, they show you all kinds of interesting information about these numbers, which we're going to see in a second. So let's take, for example, and by the way, here's some notation that's useful. So we typically write a sub k minus 1, all the way down to a sub 0, and then we put a subscript b for this expansion. So for example, to help illustrate this, 23 we already found is 1, 0, 1, 1, 1 base 2. Let's do another one. Let's say we had 245. Let's think of this in base, say, 8. So what are the powers of 8 that go into this? So you have to ask yourself, what's the largest power of 8 that will go into 245? So you ask yourself, okay, 8 squared is 64. What's 8 cubed? Well, say you don't know that in your head. Say you go to a calculator and say 8 cubed. 8 times 8 times 8. and you say, oh boy, that's too big, that's 512. So we can't do that. So we know the largest power that can go into 245, the largest power of 8, excuse me, is 8 squared. Now, how many times does it go in there? Well, you ask yourself, divide it in. How many times does 64 go into, how many times does 64 go into 245? If you can't do that on paper and pen, go to a calculator and say 264 divided by 64. Excuse me, 240, I'm losing my mind. I would have messed that up. 245 divided by 64, excuse me. And it goes in 3 times. And then what's the remainder? Well, then you got to do that. No, it doesn't go in 3 times. Am I losing my mind? Right. So losing my mind. So what's the remainder? If I do 3 times 64, what's left over? Well, what's left over is 192.
Isn't 53 left over?
I'm asking you.
No, 3 times 64 is 192.
Right.
And then one at the
So then
remaining.
what's left over? Okay, be
53.
careful now. Be careful. Be careful. See, you're already, this is what's beautiful about it. You're already doing it wrong. What should I be writing here? See, this is very good. See, here's how we learn. And this is why you have to, and I can't express this enough. What we have to do is we have to get out of trying to memorize procedures. This is such a bad way of learning things. What we're trying to do right now is we're trying to do the opposite. I'm trying to take something that's in base 8 and write it in base 10, for example. What I have here, this is not the number 245.
Oh, would it be?
Yeah, see, you guys are just like zombies. You're just like, oh yeah, I'll just do. That's not what's happening here.
That's so rude.
This is how we learn. What does this mean? This notation means 2 times 8 to the power 2 plus 4 times 8 to the power 1 plus 5 times 8 to the power 0. That's what that means. Man. Quit trying to memorize things. Save that for the computers.
Wait, explain that a little bit more.
That's exactly this subscript of 8 means this is not base 10. This is not 245. This is 245 in base 8, which means the coefficients are 2, 4, and 5. And then the base is, you think about this, the power here is, so this is the 0 power, the first power, and the second power. And if you do the arithmetic now, this takes you to 156. So the number 156 written in base 8 is 245. See, this is it's very confusing.
Now I'm confused.
I know, because look at these 2 examples.
Mm-hmm.
On the first example right here, I'm going from base 10 to base 2.
Mm-hmm.
Here I went from base 8 to base 10. So when you see parentheses around the number with a subscript, that is not the number that you know and love. That is a different representation of that number.
Oh, I thought we were, okay.
Yeah, see, you're going the other way. So in example two, we're starting in a different base, and we're trying to find its normal or its base 10 representation. Do you understand that now?
Yeah, that makes more sense.
Here, let me help you. Let's do another example that will help clarify, I hope.
We did this in my intro to ed math class.
Yeah, right. So what if I did something like, I don't know, how about 2, Let's do it in different. How about we do, what was the number we just did? 245. Let's do it in, now let's do this number in, instead of base 8, let's do it in base, let's see. How about we do base 6? So now we want to write this as powers of 6, right? Do you understand that? So what is this in powers of 6? Well, this would be 2 times 6 to the second power plus 4 times 6 to the first power plus 5 times 6 to the 0. And of course, if you go and you plug this into a calculator, so this would be 36 times 2, so that's 72 plus 24 plus 5. And if I go put that into my calculator, I get 101. If I didn't make a mistake. And so now if you went to Google, for example, and you said Google, here, let me show you. So let me share this with you. Go back here. If I went to Google and I said, if I said 101 in base, what was it, base 6? You would see that 101 in base 6 is 245. So in base 10, 101, but in base 6, it's 245. And that's exactly what we showed. We showed that in base 6, the number 101 is 245. So this takes some practice and getting used to. But luckily you have help because you can always use the Google machine to help you. When in doubt, ask the Google machine. When's my B-Day? The hell does that have to do with anything right now? What is happening? December 14th. You guys will long be out of my life. What's the decimal, or what's the base 8 representation of the 14? What a time to be alive. By the way, there's a very nice algorithm for doing this. And maybe we'll let you, I can even share some code if you want. You can write a little program to convert numbers. Here, let me go. Actually, I'll show it to you now. Let's see if we can pull it up. Let's minimize this. So it's not hard to do this. Let me go to, what is hard is for me to hide my screen when I stop sharing for a second. That's the key. Open up Octave. That's not what I wanted. I gotta find it. Maybe I don't remember where I put it. Oh boy. Let's see if it's in a different. Let's see if it's somewhere else. It's not there. Where did it? Oh, well, I can't find it. So I'll have to find it for you and I'll share. I thought it was in that folder. I'm not going to waste time looking for it. But anyhow, it's quite simple to write a little bit of code that does this. And I can share it with you if you want. Does anybody have any questions or comments about this? I don't know, is it? Is that, yeah, it's in one of my folders. I don't know which one it's in, but it's really, it's a simple code. It's like 3 lines. And the quick way of thinking about it, probably the best way to think about it is to think about what I kept saying about what's left over. So we have these ideas, we can use remainders, and just kind of like just divide and conquer. All right, so okay, what do we care about this for right now? You know, what does it get us other than it's something that's unique? So what's an application of this? There's plenty of applications, but let's look at one that's not too terrible to understand. So there are, you know, too many to name. There's too many applications. So let's talk about 2. The first one is divisibility theorems. What I like to say, shortcuts. So here's a theorem. Let n, and we're going to write it in base 10 right now. So let n, what's the best way of doing this so that we're not confusing the masses? That always drives people nuts. So let n equal, we'll say, we'll call it D1, or excuse me, dk, d sub k minus 1, all the way down to d sub 1, d sub 0. Be a positive integer in decimal expansion. So again, I keep using this, but decimal means base 10 expansion. So if 3 divides the sum d sub k plus d sub k minus 1 all the way down to d sub 0. If 3 divides this, then 3 divides n. So this looks like a scary way of doing this, but let's just look at an example real quick to clarify it. I already did with 27. Let's write that down again. So if n equals 27, well, note since 3 divides 2 plus 7, we know 3 divides 27. Let's look at one that's not so obvious. How about we say n equals 2705 1. So since 3 divides 2 plus 7 plus 5 plus 1, which is the same thing as 3 divides, well, this is 6 and 9, that's 15. We get that 3 divides 2051. Now, the proof of this is you just write out the number n and it's base 3, and then you just look at it's pretty. Maybe we'll ask you to do that for homework. It's not a difficult proof. Does anybody have a question about this? And you might remember some of these. Mackenzie and Kayla, if you guys would teach it, taking classes for elementary school, these are topics that are taught. Like, when is something divisible by 3? When is it divisible by 5? When is it divisible by 7, 11? There's all kinds of these little tricks that you can do. And the proof of why they're true is all based upon these ideas. So, for example, you know a number is divisible by 5 if its last digit is 0 or 1. Right? 0 or 5. Okay. So another application of this is computing. What happens oftentimes is we have to compute these things. So we have to compute b to the power k for some number k mod n. In particularly when these things are all very large numbers. So what happens, particularly in things like cryptography, is, we need to divide a large number to a power, and we're going to divide that by a large number. Right? And it's something that's technically, I want to say technically, but it's in, for humans, it would be an impossible task. And for a computer, it's not an easy task either. And so we need quick, efficient ways of doing this. And so here's one of the ways that you can do it. So suppose we have some number, what do we want to call it? Let's say we want to compute, or let's not just say, so consider this. Let's put it this way. So suppose I'm going to pick an integer, and I want to use a different letter. So suppose I have k, and let's suppose that it's equal to some binary thing. Let's say it's a sub, I'm going to have to use different letters here, so bear with me, because k is now representing a number. Or how about, instead of that, let's use, I got an idea. Let's call this m. No, we called it k up here, so let's switch this out, because I don't want you to, I know as little as children here. Let's rename these things. That way we can stick to the numbers we've been using. So it doesn't matter. I could have kept it that way, but let's use this as power n, and we'll call this mod m. And so let's say that this is b, n, and m are large. So for sake of an argument, let's suppose that we have some number n, and it has a decimal, excuse me, a base 2 representation given by this. Now, if I take number b, take my number b, and I raise it to the nth power, how can I, what can I do? Well, what is this equal to? We know that this is equal to b raised to some scary power. What is the power? Well, it's a sub k minus 1 times 2 to the power k minus 1 plus a sub k minus 2 times 2 to the power k minus 2. And then you come all the way down to here, you get a sub 1 times 2. And then you get plus a sub 0. But you have exponent properties that say you can rewrite this. You can rewrite this as b to the a sub k minus 1 times 2 to the power k minus 1, and then that's times b a sub k minus 2 times 2 to the power k minus 2, and then this process goes all the way down to b to the power a sub 1 times 2 times b to the a sub 0. Now, why is this significant? What does this matter at all? And by the way, actually what we should do is we should do this right away for an example we had, just with smaller numbers to illustrate. So I know this is kind of scary looking, but let's do that. So don't get overwhelmed with all these subscripts. I know it is overwhelming, so it's not fair for me to say don't get overwhelmed. Let's look at an actual example. So let n be 23, and we know what that is in base 2. It's 1, 0, 1, 1, 1, right? Or not base 3, base 2. Now we want some number b to the power 23. So instead, we're going to look at b, and we're going to raise it to 1 times 2 to the what power? What power is that? That's the 4th, right? Plus 0 times 2 to the power 3 plus 1 times 2 squared plus 1 times 2 plus 1 times 2 to the 0. And now I can break each one of these up. So here I get b2, the 2 to the 4th, plus this is just 0, so I ain't worried about, or excuse me, let me be more careful. So this is plus b to the power 0 plus b to the 2 squared plus b to the, excuse me, these aren't pluses. I'm losing my mind. These are products. By the way, I'm acting like it's obvious, and it might not be obvious to you. So let me remind you what property of exponents I'm using here. What I'm using is I'm using this thing you learned as a kid. If I have some number, let's say it's x to the a times, or excuse me, a plus b, this is the same as x to the a times x to the b. That's what I'm using here. So what this means, if you think about it, is this means that the only thing that matters when you're computing b to the 23, what this does is this comes down to computing these things. B times b squared times b to the 4th times b to the 8th, all the way up to any power of 2. So again, you have to imagine that the numbers we're dealing with here, b, and instead of 23, you actually have a very large number. Maybe it has hundreds, thousands of digits in it. And from a computation standpoint, it's much more efficient to do it this way. And then we have this idea of modular arithmetic. So if I wanted to figure out what b to the 23 was mod some modulus, I can just do each piece separately and then multiply them together. Does anybody have a question about this? Questions, comments? So again, let me reset the scene. In many applications of what we're calling this as number theory, and considering or including the one that we said is, very important, that is this idea of cryptography, we need to often determine b to the n mod m, where these numbers are large. And so what we can do is we can use the binary representation of the exponent to sort of take a shortcut. And it's not just a shortcut for the human, it's actually efficient for the machine to do as well. It's quite fascinating, actually. if I go to a computer, let's do an example maybe. And hopefully we can finish it before the end of class. So we're running out of time. If not, we'll let you finish it. So here's an example. Let's compute 3 to the power 23 mod 51. So if we go brute force, if we just follow sort of what we were saying, so we know that 3 to the 23. Again, if we look at our previous page, this is 3 to the power 8 times 3 to the 0, right? So again, I'm just reading off these things, times 3 to the 4th times 3 to the 2nd times 3 to the 1st. Or not, that's not 8, that's 16, excuse me. So this is the 16, this is 2 to the 4th, 2 to the 3rd, yeah, 2 to the 3rd, 2 to the 4th. So it'd be 2, and then of course this would just be 1. So now what we can do is we can take the mod of each one of these. 51. The idea. Now the nice thing is this number's 9, so it's just itself. So if I take each piece, so So 3 to the 23 mod 51. I guess I shouldn't write it like that. We think if we're thinking reasoning, we would think this would be 3 to the 16th mod 51 times 3 to the 0 mod 51 times 3 to the 4th mod 51 times. Now again, I don't, these guys at the end, this is just 9 and this is just 3. So this one is going to require a little work. This is just 1. This one we think might require some work. And then of course we have times 9 times 3. It does. I'm going to find out the final answer. Let's see if we did it right. All right, so what's 3 to the power 16? Well, that's actually a big number too, right? I mean, 3 to the power 16, what is it mod 51? We might have to do some work there. So by the way, what I did suggest to you last week is, you know, it's not a bad idea to get comfortable using calculators to do this stuff, or having, there's lots of places on the internet that'll do it for you. Wolfram's one. But you're going to need a calculator to even begin to understand 3 to the power 16 mod 51, right? Unless you really sit around and do long division. So what I'm doing is I'm just going to use a calculator to ask myself that. So if we do this correctly, we get 3 to the power 16 mod 51 turns out to be 18. And then this is times 1. And then what about 3 to the power 4? Well, that's 3 to the power 4 is 81. So if I take the remainder when I divide 81 by 51, so 51 goes in 81 one time with a remainder of 30. And then, of course, we have 9 and 3. So let's note that these guys are, if I multiply these creatures together, barring I didn't make an error, you have 18 times 30 times 27. So that number becomes 14,580. Now, we want to know the remainder of this number when we divide it by 51.
Sorry, Professor?
Yes.
Sorry, how do we get 18 again?
What is the remainder when you divide 51 into 3 to the power 16? Remember, this notation means the remainder of this number when you divide it by this number. So we're out of time. We're actually over time. So we're going to have to finish this on Wednesday. But what I would tell you to do is think about it. So if you go to a calculator and you say, okay, what is, take the number, you have to, it's like a guessing game. It's not, you have to ask yourself, how many times does 51 go in 3 to the power 16? And then you look at what is the remainder in that. So we tried to show you how to do that on last week. You can keep reducing it down. You can go one step at a time, but you might want to review the notes from last Wednesday. But we have to finish up because we're over time. And if you want, Tom, we can sit there and talk about it, or you can come to my office and we can go over it, and I can sort of give you some more examples of what's happening, or we can Zoom it.
Okay, I shot an email last week for a Zoom meeting.
Yeah, I did see that. Yeah, well, I'll have to respond to that. My apologies.
Okay, thank you. Yep, no problems.
Does anybody have a question about this before we're done? And by the way, if this thing right here is equal to 45 modulo 51. So the correct answer is 45. And we'll go over this again. We kind of rushed it, so I feel bad, but we'll go over this again on Wednesday. All right. All right, guys, I apologize for rushing at the end, and I apologize for going over. Be safe. I will see you guys Wednesday. Thank you very much, and take care.